сегодняшний докладчик Луиджи Аккарди. Название доклада Characterization of product states on polynomial algebras in terms of scalar products of n-particle vectors. Please.
Okay. So first of all, I want to express my deep gratitude for invitation to speak in this institute. I feel now a kind of external member of this institute because I have so many collaborations with many of you, and so it's always a great pleasure for me to discuss this problem, especially because I was thinking to explain a little bit the logic that has brought us to analyze these problems. Because the paths of mathematics sometimes are very, very contorted. They are by far not piecewise linear. And in fact, if somebody would have asked me, when we began to work with Igor Vassilievich and with Sergei Kozyrev, with Irina Refeva, with Alexander Peshin, about and many others I did not mention now, but when we began to work on the stochastic limit, we were attacking very concrete physical problems. And we would never imagine that such strange mathematical structures would come out from these very concrete models. I want to mention two examples of these very concrete mathematical structures that a posteriori have turned out to be really fundamental mathematical structure. One is the emergence of Hilbert modules as canonical state space for strongly nonlinear quantum system. Another is the notion of interacting Fock space. A posteriori, it is very natural what is an interacting Fock space. Interacting Fock space is simply the most general framework in which you can speak of creation and annihilation operator, which are related only by one fundamental point, property, that annihilation is the adjoint of creation. This seems to be a very vague condition, but you cannot imagine how rigid it is. And another point, which was at the origin of the program of nonlinear quantization, was the proof, absolutely surprising, that all classical stochastic differential equation and quantum stochastic differential equation can be formulated in much more intrinsic way, just as white noise Hamiltonian equation. This is completely unexpected, even in classical probability. If you take a Ito equation, no probabilist suspected that an Ito equation is in fact a white noise Hamiltonian equation. Moreover, all possible stochastic differential equation driven by standard semi-martingales, well, they are completely covered by the first power of white noise, quantum white noise, and the first normally ordered, the second, A daga A, so the normally ordered second power. Now, when we discovered this, we asked ourselves, okay, but if all classical and quantum stochastic equations are covered by the first power, A daga, and by the only normally ordered A daga A, what kind of equations will be defined by nonlinear powers of fields? And this immediately brought us to the renormalization problem. Because it's very well known, and physicists know this since practically almost 100 years, that when you go to higher power of fields, you get singularities that you have to correct with the different procedures that go under the common name of renormalization. But also here, something very strange came out, because we gave a new approach to renormalization. So while in physics, you introduce renormalization in interaction, in our approach, it was very natural for us to change the game of the rule and to introduce renormalization at kinematical level. So instead of starting with a field, standard field, which we call now linear field, for the reason that you will understand later. So if we start with a standard field and introduce a nonlinear interaction, and this is the standard procedure. In our procedure, we introduced a non-standard field, defined by nonlinear, typically nonlinear power of a standard boson field. And we were able to realize, in the simplest non-trivial, in the simple power non-identical equal to 1, the square. Well, our original proof was very hard and was not explicit. We simply could prove that quadratic Fock quantization exists. But we had not the explicit formula. And I want to show you, I have written to show you how, even such a weak nonlinearity like quadratic 1 can completely change the structure. So I have written for your use the scalar product of the n-particle space in the renormalized quadratic quantization. This formula was not discovered in our paper with Lu and Volovich in 1999, but it was discovered many, many years after. With a story which is too long to be described today because I have to speak of other things. So you see, I have written this formula to show the difference between the usual boson scalar product that you recognize in the term, that this term corresponds when in this sum only the index I1 is equal to n and all the other indices are equal to 0. You see? The other formulas, you see, in the other formula, what you notice? First, fundamental difference. This we already understood and we emphasized in our paper on renormalized quadratic quantization with the Volovich and Lu. We emphasized that while in first order quantization, you can take general Hilbert space, so the only vector space, Hilbert space structure is important. In quadratic quantization, it's absolutely essential that the test function space is also an algebra. And there's also an involution. And in fact, you see here in the scalar product that the powers of the test vectors appear. So, for this reason, you need the test vector must be algebra, not only vector space. So you see, now this is the scalar product. Now, the quadratic quantization is sufficiently well understood. We can speak of quadratic Fock space. We have some preliminary result in the case of equilibrium quadratic states. And this is a paper joint with Amosov and France. And recently, we have gone further in constructing the quadratic analog of Bogolyubov transformation, which are rather difficult. I have no time to discuss this. Now, the problem is this. Why, from quadratic quantization, starting from the cube, is well known that there is a jump in difficulty, and our development brought us to discover totally unexpected connections. For example, when we try to apply our renormalization approach to higher powers of white noise, we discovered a kind of second quantized version of the Virasoro homologic of Lie algebra. So it is clear that this direction is a direction that is related to important problem in application. But I want to speak not of connection with application, but connection with pure mathematics. So the connection with pure mathematics was first hinted in 1998 in a paper of myself and Bozzeico. Bozzeico is a person in harmonic analysis. In this paper, we discovered that if we take the most trivial interacting Fock space, so-called one mode, in physical language, they would correspond to a system with 1 degree of freedom. And in mathematical language, they will correspond to polynomial in one real indeterminate. Okay? Then these objects, polynomial in one real indeterminate, and we suppose that on this polynomial it is given a measure which has all moments. So this is, in algebraic language, the same to say that we have a state on the star algebra of polynomial, because star algebra of polynomial, I will give a definition in a moment, is a natural structure of star algebra. So these objects are categories, because there are natural morphisms, both in interacting Fock space and in orthogonal polynomial. In this 1998 paper, we discovered that the two categories of one mode interacting Fock space and one variable orthogonal polynomial were isomorphic. So they are essentially two languages to speak of the same thing. So this immediately brought the idea, the hope that the same would be true for for polynomials with a higher number of variables. Well, it took 16 years to clarify this situation, but the answer is negative in the sense that starting from a number of variables greater or equal than 2, the theory of orthogonal polynomial corresponding to this number of with d indeterminates, with d greater or equal than 2, can be characterized. They are interacting Fock space, but first of all, they are so-called symmetric interacting Fock space. Second, there is an additional condition which is very difficult to formulate and which has to do with the multi-dimensional version of Favard lemma, which didn't exist until 2000 16, because it is probably the most important, the Favart lemma in one variable. Essentially, when you have only one polynomial in one variable, you associate to then two sequences of real number called the Jacobi sequences. And the Favart lemma is the converse, is the reconstruction theorem, which says that given two sequences of real number, with one of them has to have a certain additional property, then there exists a unique state on the polynomial algebra. And then we know from classical analysis that there are many measures that can induce the same state on the polynomial algebra. This is the famous Hamburger moment problem for the full real line. So, what happened? When you have the orthogonal gradation, when you have orthogonal polynomial, you have the orthogonal gradation. And of what? Since you have a measure, the integral of these measures induces a state on the polynomial algebra. So, you have a state on the polynomial algebra. And the scalar product of the orthogonal gradation is the scalar product induced by this state. Okay. Now, the problem is whenever you have such a structure, you canonically have a quantization procedure, a generalization of the quantization procedure. And I want to try to explain why. That is, why, starting from a very classical part of classical analysis, the theory of orthogonal polynomials, then you are necessarily brought into a construction which generalizes standard quantization. So let me go a little bit quicker now. So the algebra of polynomials in D variables, D can also be infinite, and this will include quantum field theory, when D is infinite. But it's better to think of D finite, because it will avoid to speak of domain for unbounded operator. And so I will never speak of domain. So essentially I am speaking of bounded object. So what I want to do, I want to not to speak of the algebra of polynomial in abstract, algebraic language. I want to realize the polynomials as concrete functions. Because I want, for later application, that the coordinates, the independent variable of the polynomial, become random variable. So I want a concrete functional realization of the polynomial. What is usually done is to consider polynomial, a random variable with values in a real vector space. Typical example are D. So this will correspond to polynomials in D variables. When you have a real vector space and you have the algebraic dual, there is a canonical embedding of the space into the bidual, that is the dual of the dual, which is given by the so-called coordinate functions. The coordinate maps is a function defined on the algebraic dual, and which to an element of the dual simply associates the element evaluated in the vector, test vector, that indexes what later on will become a random variable. At this level, we are purely algebraic. There is no statistics, no measure theory. Okay, so we have these random variables that we realize as a function from x with value in R and y in R, because the vector space is real. So the duality as real valued. However, we take the complex. Since they are functions, we can take the algebra of polynomials in these functions. And we take the complex algebra of polynomials in this function. Okay? Then since the coordinates are real valued, since they are functions defined on a set and with values in R, the polynomial are defined on a set and with values in the complex numbers. So whenever you have functions with values in complex numbers, you can multiply them, you can add them, and you can take the complex conjugate of any value pointwise, so you have a star algebra. So the polynomials on the vector space V have a natural structure of star algebra, and since the coordinates take real values into real value, when the vector V is in the real space, the associated function, coordinate function, is Hermitian. Now we introduce probability. We take the sigma algebra generated by the coordinates, which is a sigma algebra in V star. And then we suppose that we give a probability measure. Then this becomes, the coordinate function become random variable, because I have, they are all defined on the same probability space. So this is the standard definition of a stochastic process, of a random process. So we interpret this, since this gives a linear function on the dual, we can interpret as a classical random variable with values in the vector space. When you take the simple the evaluation in a single test function, then you get a scalar value, a real valued random variable. So essentially, a vector valued random variable is what is usually called a random field. That is a map, a linear map, which to an element of a vector space associates a random variable. Now in the finite dimensional case, typically we identified V is isomorphic to a real finite dimensional vector space, so essentially is identified with RD. And so we are speaking of measures on RD. Okay? And so essentially we have a probability measure not on V star, but also on V itself. Now we introduce the property that all moments exist. This property means that the monomials, and therefore the polynomials, are integrable. They have a finite value. Okay. So, from now on, for me, random field will mean random field with all moments, for all V and all N. This must be integrable. Okay? And now we fix the vector space, so sometime I will omit from the notation. Now, since I have this measure, I have the associated integral. And I use the same notation for the measure and for the linear functional defined by the integral. And there is a standard way, when you have a state on a star algebra, to define a semi-scalar product. Here is written prescalar product. It is more precise to say semi-scalar product, because there can be, and in many important cases, there are zero norm vector for this scalar product. Okay? So if you want to complete, you have to quotient the zero norm vector. So, for example, we can speak of probability measures on manifold, because the manifold is embedded into the vector space, and the support of the measure is the manifold. This theory includes, and has very nice connection with algebraic geometry, but again, I cannot discuss it now. So, what we have? One, we have this integral, which is a linear functional, but it is a linear function which is positive on positive polynomial, and it preserves the identity. So this is what is called a state in algebraic probability theory, and also in quantum mechanics. In fact, algebraic probability theory takes it from quantum mechanics. So we have a star algebra, which is the polynomial algebra. A positive, normalized linear function on it, and this is called the classical algebraic probability space. When instead of this algebra we take a non-commutative algebra, we speak simply of an algebraic probability space without class. Classical is because the algebra of polynomial is commutative. Okay? And now this theorem is very important, simple proof, but important, because it says among all scalar products on the polynomial algebra, which scalar product are obtained come from a state using this formula. And the characterization theorem tells, okay, normalization is expected, but the characterization theorem tells that a scalar product has this form for some state on the polynomial algebra, if and only if the multiplication by coordinate map is Hermitian, not only for the star algebra structure. So the involution in the star algebra must be compatible with the involution given by the scalar product. If I have a scalar product, I have a natural notion of adjoint, but a priori is not clear that it must be the same as the involution in the star algebra. This is a necessary and sufficient condition for the scalar product to have this form. Okay? Now, once I have an algebraic probability space, I have the cyclic representation of this algebra induced by the scalar product. So I complete the algebra by the scalar product given by the state, and I get a Hilbert space. I have an embedding of the algebra into this Hilbert space. I have a representation of the multiplication operator by this algebra into the adjointable linear operator, which are densely defined on this Hilbert space. And I have a cyclic vector, which is simply the embedding of the identity into the Hilbert space. So I have now these three objects. I just want to mention for the analysts that are present here that this space H phi is contained in L2, but usually is not, because it's the completion, L2 completion of the polynomials. And it is very well known that if the moment problem for the measure is not unique solution, this inclusion can be proper. Okay? For standard measure, we are accustomed to Gaussian, even Meissner. This doesn't happen. You have equality here, okay, for standard case. But there are many important cases where you have not equality. And, well, for example, a non-trivial example where you have not equality, the moment problem is not uniquely determined, is the power of the Gaussian, the k power of the Gaussian, starting from k equal 3. For that, the moment problem is not determinate. Now, a last point, very important, but last. Once you have the algebra of polynomial, you have a natural filtration. What does it mean, filtration? Take the polynomials of degree less or equal n. So, of course, the vector space of polynomial of degree less or equal n is contained in the vector space of polynomial of degree less or equal than 1. Moreover, if I take any coordinate, any, and I multiply this any polynomial of degree less or equal than n by any coordinate function, I get a polynomial of degree n plus 1, by definition of degree of polynomial. So summing up, this is interesting that the algebra of polynomial is identical to the algebra, by definition of algebra of polynomial, because a polynomial is a finite sum, a linear combination of monomial. But if we consider this as a Hilbert space, then you must take the closure in infinite dimension. It's not true that is set theoretically union. Now, so we have seen that once we gave the gradation, increasing filtration, the polynomial algebra and the state on it, we only consider state that come, a scalar product that come from states. So we have this abstract, very abstract scheme. We have an increasing sequence of Hilbert spaces with the projections corresponding to them. We have a family of self-adjoint, let us say Hermitian operator, which in the specific example of orthogonal polynomial are just multiplication by coordinates. And this multiplication by coordinates are filtration increasing by 1. So this is a completely abstract scheme. I need only these three properties. Increasing filtration of Hilbert spaces, associated projection, self-adjoint operators, which are gradation increasing by 1. What is the theorem? The theorem is this. If you have this increasing filtration, this is a very standard fact, you associate a set of mutually orthogonal projections by simply taking the difference. This is standard. But what is non-trivial is that the tridiagonal, this is an algebraic formulation of the tridiagonal Jacobi relation. Because you can consider Yj is an Hermitian operator. Pm on the right multiply Pn on the left, on the right and Pm on the left. So this is just the matrix element Mn, the generalization of the matrix element. If the projections are rank 1, this is simply a multiple. The multiple is exactly given by the matrix element. So the Jacobi relation tells you that this matrix element is 0 unless M is equal n minus 1, n, or n plus 1. So this is a tridiagonal. It's a matrix with operator coefficients, you can think. And this tridiagonal. Okay? Of course, if you, in addition, and in the case of polynomial, orthogonal polynomial, this is always true, that the filtration increases to the identity, because any polynomial will be, and in fact this limit is in a very strong sense, then this sequence of mutually orthogonal projection sums to the identity. In the same topology, if we have infinitely many. So you see, from the Jacobi tridiagonal relation, it follows that I have this, which is more similar to what you find in orthogonal polynomials. This is called the symmetric Jacobi relation. In orthogonal polynomial, in mathematics, it is more used so-called monic tridiagonal relation. In physics, the symmetric tridiagonal relation are used. Okay? So this is a formulation of the tridiagonal Jacobi relation. Now, I have a partition identity, so I can sum over n. On the left-hand side, the sum over Pn is 1, the identity. So I get Yj. But on the right-hand side, I get the sum of operators which are very special. So, why? Because the first operator takes from Pn and goes to Pn plus 1. The second operator is diagonal, takes Pn and remains in Pn. And the third operator takes Pn and brings to Pn minus 1. So, by analogy with the physics language, it's very, very natural to call creation, preservation, and annihilation operator these three objects. Okay? So you see, let us sum up what we did. We started with a completely abstract structure, an increasing filtration, a family of self-adjoint operator which increase by 1 the gradation, the filtration. And automatically we have that these operators are the sum of three operators. One is gradation increasing of degree 1, another is gradation preserving, and another is gradation decreasing of degree 1. And you see that since the yj are self-adjoint, you see that immediately, if you take the adjoint of this, you will find this. That is, the adjoint of creation is annihilation, and this in the middle is self-adjoint. So mathematics tells you, so in physics you typically interpret y as a field operator, but there is no this term. This term is never considered by physics. But because gradation preserving operators in physics are typically considered belonging to the dynamics, not to the kinematics. But we know that this is not true. There is a theorem that tells you that the random variables are symmetric in the sense that they are invariant under the reflection with respect to the origin of the vector space, if and only if this middle operator is 0. So the fact that in physics they consider field without preservation means that they restrict to symmetric random variable. But why? For example, take the Gaussian. The Gaussian, of course, is symmetric, the standard Gaussian. But take the square of the Gaussian. So if you want to, remember, we want to do nonlinear fields. We want to do power of typically Gaussian field, because Gaussian fields correspond to boson. The square of the Gaussian is not symmetric. So the square of the Gaussian has a non-trivial preservation operator. Okay? So just if you want to speak of quadratic fields, you necessarily are led to take non-symmetric objects. Of course, let me rush because I see that time is consuming and I am not arrived to the key point. So you see, summing up, if we have this with Hilbert space, increasing filtration, self-adjoint that increase filtration of degree 1, then it's equivalent to give an orthogonal decomposition and a certain map from the space Aj, which go from Hn to Hn plus 1. So, 1. So, increasing of the gradation of degree 1 and the preservation operator. This is, but, for this reason, motivated by this reason, we call this object generalized creators, generalized annihilator, and generalized preservation operator. Okay? And they call cap operator creation, annihilation, and preservation. Now, okay, this three-diagonal I said already is called the Jacobi relation. And what is important is that the quantum decomposition of individual operator will be unique, up to unitary isomorphism. Another important corollary, the type 1 commutation relation. If you have this structure given by gradation, orthogonal gradation, and increasing by one operator, decreasing by one operator, then these products, the two products, are gradation preserving. So the commutator will be a certain operator in general. Is a kernel, because you see the index yj are the index of the coordinates. The index y, you should think, when you think of coordinate function, to x evaluated in ej, where ej is a linear basis of the vector space of test function v. So the right-hand side is a gradation preserving operator, and is a kernel. Now, what can we say about this kernel? Well, there are many. The crucial point is that this is a commutation relation canonically associated to such pair, orthogonal gradation, creation map, creation operator. Whenever you have this, you have a commutation relation. These are called type 1 commutation relation, because there is a new type that requires much more, and I will tell you later. So the type 1 only mean that the two are gradation preserving. Nothing else is needed. Now let us see how this is related to the topic of my talk, product states on polynomial algebra. If I have a polynomial algebra in d variable, take d to be the finite number, from 1 to d, small d, the capital D is 1 to small d, okay? Then, you see, I take a linear basis, let me take a linear basis of the vector space V. Then, by definition of linear basis, V is the vector space direct sum. This dot means vector space direct sum. There is not yet Hilbert structure. And the algebra associated to the coordinate of the test vector En is exactly an algebra of polynomials of one variable. They are contained in the algebra of all polynomials in any variable. Moreover, they are algebraically independent. That is, they have trivial intersection. In fact, here I should have put multiples of the identity, C times the identity. And moreover, they linearly, in algebraic sense, span the algebra of all polynomials. This is true also in infinite dimension. Okay? And these products are such that the n factor belongs to the algebra in the nth variable, and the product has only a finite number of non-identically one factors. Okay? At this moment, I say that a state is called the product state if, when I restrict the state, if there exists a linear basis, such that when I restrict the state to the one-mode algebra means is isomorphic to the polynomials in one variable, in one real variable. So for each n, Pcn is isomorphic to the polynomial in one real variable. And phi n is thus a measure on the real line. I say that it is a product state if the expectation of the product is the product of expectation. In probabilistic language, the random variables corresponding to x, en are independent we should now say tensor independent or classically independent with respect to the state phi. So the product states are the simplest possible states. How this is related to commutation relations? This is related because if you remember, when we wrote the commutation relation of type 1, we wrote that this is an operator-valued kernel. That is, it is sesquilinear in V and U. So this is what is called in mathematics a Hilbert module. It's a scalar product, but with values in a star algebra. It has positive definite in the usual sense, but a positive definite in the sense of the star algebra. So essentially, this is a module structure. The simplest module structure is when this is not an operator, but a multiple of the identity. This is the simplest possibility, okay? In this case, you can easily verify that this sesquilinear form, which is now scalar valued, must be positive definite. This is a simple calculation, very elementary, but I have no time to insist on it. So I have a semi-scalar product. Remember, semi-scalar means that there can be zero norm vector. What is the interesting theorem is this. Essentially, the scalar characterize what in physics is called the free Bose field, and in classical probability is called the standard unit Gaussian process on the Hilbert space given by the scalar product coming from the commutator. So let us say the theorem. The theorem precisely is this. Take a real vector space and take a sesquilinear, a semi-scalar product on the complexification of V. Because remember, we take complex valued polynomial. So we need the one particle space is isomorphic not to V, but to the complexified of V. So we want it, of course, not to be identically zero, otherwise the Hilbert space is zero. Suppose it's not identically zero, this Hilbert space. Then the following statements are equivalent. The cap operators canonically associated to the classical random field X satisfy the scalar commutation relation. The second is the quantum field that is A plus A minus canonically associated to the classical random field, as I have shown before, that every classical random field canonically defines commutation, creation, annihilation, and preservation operator. So the quantum field is the standard Fock boson field, but over which Hilbert space? Over the completion, on the complexification of V under the given scalar product, semi-scalar. So I have to quotient out the zero norm vector. And the third is X is the standard unit Gaussian field on the real Hilbert space, because now we are in the domain of classical processes, which again is taken by taking the quotient, but this time you take the quotient not of the complexified of C, but of V, but of V itself, because V is real. The standard unit Gaussian process is defined on real vector spaces. So you see this is completely equivalent. So we see that if we consider this general quantization structure that canonically emerges, you see that is the in the simplest possible case, you get the usual quantum fields. So you will intuitively understand that, and moreover, look, from this you very easily see that if the two vectors u and v are orthogonal, the corresponding creation and annihilation operator commute. And there is a theorem, I will formulate here, that says that this property, that creation and annihilation corresponding to different degrees of freedom commute, characterizes the product measure. So the commutator to be scalar characterizes the Gaussian measure, which is a product measure, a particular, very particular product measure. But if you relax and you only require commutativity of the cup operators corresponding to different indexes, j and k, of course this cannot be true, otherwise there is no trivial commutation relation, and you prove that this is only for the delta field you can have, the field whose distribution is concentrated on the zero, so a trivial field. So this property is very important. I insist, it can be, this is of course verified in standard quantum mechanics. But you understand what you deduce from this theorem. You deduce that if you want a quantum mechanics associated to a non-trivial measure, which is non-product, then this property you cannot expect. But this property is everywhere used in physics nowadays. And the last characterization is this. I conclude. Now, the last characterization is this. We have spoken of what happened at different degrees of freedom. Now, in standard quantum mechanics, you have another important property. You have this property. Suppose that you have a quantum system with d degrees of freedom. And then you, for each one and d, you define the associated creator and annihilator. You can imagine they are this different type of particles that you create. Particle of type 1, type 2, type d. Now, the property I mentioned is this. Of course, if this m1 equal n1, md equal nd, then you get the norm that in the product case is a product. But if this multi-index n1 and d is different from the multi-index m1 md, in standard quantum mechanics you have orthogonality. Now, it was very natural to ask oneself, is this property a characterization of orthogonality or not? And the theorem is almost a characterization, in the sense that well, we are very near to a characterization. Let me say the first theorem. The first theorem tells you that if you have this orthogonality, then the vectors, this is the n particle vector, m1, md sum to a fixed natural number n. If I apply the annihilator j, I obtain a multiple. What is the delicate condition that we need in addition? That is, here is an open problem. I will tell you in a moment. You see, this is you have the vector which has m1 particle of type 1, m2 of type 2, md of type d. And in the denominator, you have the vector which has exactly the same number, but the j particle is diminished by 1. Because annihilator of the j, this is aj, and you guess that it will kill one particle of type j. The other one, it doesn't affect. However, there is this scalar which depends on the whole index set. And the condition that it comes for having a product measure is, let me show you, is this condition. Essentially, this condition means that in fact, this depends only, you see, the k index is +1. Here the k index, but they are equal. And here, the j index is on the numerator mj, on the denominator mj minus 1. So essentially, you can prove that this is equivalent to say that this quotient, that this norm has the factorization property that you expect from product norms. So if the norm comes from a product state, this number, which a priori depends from n1 and d, factorizes as a product of norms. Now, the problem is, do there exist orthogonal polynomials that satisfy the first condition, that is the annihilator aj applied to m vector gives m minus 1 vector on the same species j as the annihilator. However, this condition is not satisfied. We can construct example with interacting Fock space, but we are not able yet to construct example with orthogonal polynomial. What is the difference? The difference is that interacting Fock space, the coordinates don't need to commute. The commutativity constraints is enormously restrictive. It corresponds to the fact in physics that fields with the real valued test functions mutually commute. So it's, from the point of view of physics, it's very natural. So you see, this is another property that we cannot expect from interacting theory, namely the fact that vectors corresponding to different numbers, multi-indices, are mutually orthogonal. Because in some sense, if we could find this example I told you, that means that there will exist a non-trivial interacting measure for which this property is satisfied. I doubt it exists, but it may be. If it exists, it will be a very interesting class of measures, because they are non-products, so they are truly interacting measures. But they are simple, because they are completely determined by scalars. So I think I can have shown you what is now the problematic that came out from the stochastic limit. As you see, we are very far from physics now, but we are, in a certain sense, we are coming back, because we are looking at standard physics from a higher point of view, because we understand from where this structure of quantization comes. And we understand that it is a very general phenomenon, and we understand that if we want to go in really interesting fields, really self-interacting fields, we cannot stick to the Heisenberg commutation relation. Impossible. So essentially, we have to rewrite the axiomatization of quantum field in view of this interacting theory. It's a strong statement, but I think that now the evidence accumulated is so much that I think any reasonable mathematician would agree. Okay, thank you.